Hello everyone. In section 2.1 we looked at solutions to second order differential equations. Now we're going to consider nth order differential equations. So we start with the definition for the general nth order. Note that because it's equal to a function of x, that it's non-homogeneous, and we'll call that equation 1, and then we'll divide everything by the function that precedes the nth derivative just to obtain a leading coefficient of 1. And basically we just change the notation to from uppercase p to lowercase p and uppercase f to lowercase f to distinguish between the different functions. And this is still non-homogeneous, but we have the associated homogeneous equation where we basically take the left-hand side and set it equal to 0. So remember, when it's equal to 0, then it's homogeneous, however you want to pronounce that. And then we have a theorem that's called the Principle of Superposition. And basically, it's just saying, so this is the formalities. These y's are solutions, and you got c's, which are constants. Then any linear combination is also a solution. So that's the idea here, as I summarized. Sums or differences or constant multiples is what we're talking about when we say a linear combination. So that's what we could see. There's sums, differences, constant multiples are the constants of c's, of course. So any linear combination of solutions is also a solution. And then we have the existence and uniqueness theorem. You could read through the formalities of that, but these are all just extensions of the previous same theorems. And basically, for the existence and uniqueness theorem, it's saying that we just have a unique particular solution based on the given initial conditions. And so we want to talk more formally about linear independence and linear dependence. As mentioned here from Theorem 1, a general solution to this homogeneous differential equation is a linear combination where all of the y's are solutions. And recall that two functions are linearly dependent, so this was from section 2.1, if one is a constant multiple of the other. And so here's a way to express that mathematically. If we say f1 and f2 are linearly dependent, then f1 is a multiple of f2, or f2 is a multiple of f1. So it follows that if they're linearly dependent, there are some constants such that a linear combination of those functions will actually equal 0. And we extend this definition to n functions. So an example that illustrates, so this is the principle, there's a linear combination of the functions that equals 0, means they're linearly dependent. So we'll see an example here where we're going to show directly that they're linearly dependent. So we've got three functions, and we say a non-trivial linear solution because obviously you could always take the constants to just all be 0, and that would be trivial. But we want to show this directly. Okay, so if they're linearly dependent, then by definition, by the previous definition, some constant multiples, linear combination of these functions, will actually vanish, equal 0. So we'll say C1f plus C2g plus C3h would be equal to 0. So that's if they're linearly dependent. So we'll just substitute in the functions, and we'll have C1 times f. So if you want it formally, C1 times 5 plus C2 times the function 2 minus 3x squared and then C3 times the function h, 10 plus 15x squared would have to equal 0. So now our job is to find those constants, C1, C2, and C3, that cause this to be true. And you might recall from Calculus 2, in particular partial fractions, we had a method where we compare the like powers. And so if I start to compare, let's say I'll go for the highest power first, compare the x squareds. If I compare the x squareds, okay, C1 is not involved with an x squared, but out of C2 I get minus 3 C2x squared, and then for C3 it looks like plus 15 C3x squared, and that would have to equal 0x squared because there are no x squareds on the right. So then dividing out the x squareds, we get minus C2 plus 15 C3 is equal to 0. Now that's one equation with two unknowns, so we'll hold on to that and just continue a comparison. And let's say next I'll compare the x's. And if I compare the x's, then we have nothing involving C1, nothing involving C2 because there's no x's there, and nothing involving C3 unless I recopied this wrong. So therefore, comparing the x's, there is no x's to compare. So the only thing we could do is compare the constants. Or I'm going to say the real numbers. And so we have 5C1 plus 2C2 plus 10C3 is equal to 0. So there's another equation, but now three unknowns. So what we're going to have to do is we're going to have to choose the value for one of the constants and solve for the other constants. So we typically would take one of the constants that appear, we're going to let one of the constants that appear in both equations equal some number, and conveniently we'll choose 1. So if we let C3 equaling 1, then we have from the negative 3t plus 15 C3 equaling 0 equation, we get negative 3C2 plus 15 times 1 is 0. So then negative 3C2 would equal negative 15, and C2 would equal 5. Okay, so now we've got C3 and C2, and then if we substitute, I'm going to do it right here because I'm running out of room. If we substitute the two values into of C3 and C2 into the equation involving all three constants, we get the 5C1 plus 2 times C2 is 5, plus 10 times C3 is 1, equaling, let me move that around, so sorry I ran out of room here. Alright, so let me kind of separate these and say that 5C1 plus 2 times C2, which is 5, plus 10 times C3, which is 1, has to equal 0. So that'd be 10, 20, 5C1 would be negative 20, so C1 is negative 4. So what you should do at the end is write the statement that 4 times F, which is 5, plus C2, which is 5, times the quantity 2 minus 3x squared, and then plus C3, which is 1, times the quantity 10 plus 15x squared combines to give us 0. And you could double check that because here's 20 plus 10. C1 was a minus 4, excuse me. So we get negative 20, here's a plus 10, here's another plus 10, so the constants vanish, and then we have a positive negative 15x squared, and here a positive 15x squared, so the x squareds vanish. So that proves linear dependence. Okay, so then the next thing to consider is a review of 3x3 determinants. To evaluate a 3x3 determinant, you should have seen this in Calculus 3, or if you took linear algebra. The easiest way is to set up the 3 rows, just recopy the given entries, and then repeat the first 2 columns. So 5, 3, 7, and 2, 6, 8. And then we take the product of the diagonals from upper left to lower right. So the first diagonal product that we have is 5 times 6 times 9, which is 270. And I'm going to choose to use parentheses. I'm going to group, because we'll do the 3 positive diagonals, and then the diagonals from lower left to upper right are considered negative in the evaluation. So I'm going to group them together with parentheses, the positives and the negatives. Okay, the next positive diagonal is 2 times 4 times 7, or plus 56. And then the final positive diagonal is 1 times 3 times 8, or plus 24. And then we subtract the diagonals that are computed from lower left to upper right. So 7 times 6 times 1 is 42, plus 8 times, see, I have the negative out in front of the set of parentheses, so it's plus, and then 8 times 4 times 5 is 160, and then the final diagonal, 9 times 3 times 2, 54. So combining the positives, we get 350, and then minus, combining the negatives, 256, gives us 94. Okay, so that's the way we evaluate a 3x3 determinant. And we define what we call the Wronskian for 3 functions. So as long as they're twice differentiable, basically for the Wronskian, we just line up the functions, first row, line up the functions in the first row, and then take their respective first and second derivatives in the second and third row respectively. And you can extend that to n functions, but we're not going to get into anything higher than 3. And regarding the Wronskian of solutions, as we saw, it's basically just a repetition, just an extension of section 2.1, where we studied second order linear differential equations, extending it to now n order. If the Wronskian is 0, they are linearly dependent. If the Wronskian is not 0, they are linearly independent. And so we'll see an example of that. Alright, so this one says use the Wronskian to show linear independence. So the Wronskian here is going to be equal to, alright, just set up the 3x3 determinant. First row is the functions. So e to the x, e to the 2x, e to the 3x in the second and third row respectively, their derivatives. I like to take the derivatives just two in a row, just go down the page basically, and take the derivative of e to the x, we get e to the x, derivative of e to the x again, e to the x, derivative of e to the 2x will be 2 e to the 2x, differentiating again, another factor of 2, so 4 e to the 2x, and similarly differentiating e to the 3x, we get 3 e to the 3x, and again, another factor of 3, 9 e to the 3x. So then to evaluate this, we'll recopy the first two columns. So e to the x, e to the x, e to the x, and e to the 2x, 2 e to the 2x, and 4 e to the 2x. Okay, and now the evaluation. So the computation again, we'll say W equals, okay, I'm going to group the positives. So we've got 18 times, when you multiply common bases, we add the exponents. So 1x plus 2x plus 3x would give us e to the 6x. Second diagonal, basically coefficients. 1 times 3 times 1 is 3, so plus 3. And again, multiplying the common bases, we add the exponents. So 2x plus 3x plus 1x is again e to the 6x. And for the third diagonal, coefficients, 1 times 1 times 4 is plus 4. And the base again of e, adding the exponents, we get e to the 6x again. And then minus, grouping the negatives together, 1 times 2 times 1 is 2, e to the, add the exponents, again we get 6x, plus 4 times 3 times 1 is 12, again e to the 6x, and then plus, last diagonal, 9, 1, and 1 is 9, e to the 6x. So that gives us 21, 25, e to the 6x, minus, it's like 21, 23, e to the 6x, which is 2 e to the 6x, which is obviously not equal to 0, so that shows by the Wronskian, I'll just say Li for linear independence. Okay, so the next thing is to consider that Theorem 1 and Theorem 2, which were basically just Principle of Superposition and the idea of a unique solution, are going to be extended to solve initial value problems to these nth order homogeneous differential equations. So some examples. It says find a particular solution given the 3 linearly independent solutions. So by the principle of superposition, say PS, we have that y equals, well, let's write it out formally. C1 y1 plus C2 y2 plus C3 y3 is a solution. And substituting, now in the future, what we're going to do, they're making it a little bit easy on us right now. They're giving us the functions that are solutions. In the future, we're going to be concerned about finding these solutions. And at this point, for this third order, we don't have the tools necessary yet. But actually we do, but in any event, just playing along with their little routine here, we'd have C1 e to the x plus C2 e to the 2x plus C3 e to the 3x would be a general solution. Now, in order to evaluate those constants, to find the particular solution, we're going to have to generate two derivatives, because notice the initial conditions, there's three of them, involving the original function, the first derivative, and the second derivative. And so therefore we'll generate two derivatives. Y prime would be c1 e to the x plus, okay, the derivative e to the 2x, again 2 e to the 2x, so plus 2c2 e to the 2x, and similarly plus 3c3 e to the 3x. And then for the second derivative, y double prime, derivative c1 e to the x is c1 e to the x. For the second term, another factor of 2 gives us plus 4c2 e to the 2x. And then for the third term, another factor of 3, 9, 3c3 e to the 3x. So now we use the initial conditions. So the first initial condition, y of 0 is 0, gives us that 0 equals, substituting a 0, the e to the zeros go to 1, so we just get c1 plus c2 plus c3. For the second initial condition, y prime of 0 is also 0, so we get 0 equals, then we have c1 plus 2c2 plus c3, 3c3. And the third initial condition is that y double prime of 0 is 3. And that gives us that 3 is equal to, and then we'd have c1 plus 4c2 plus 9c3. Okay, so when we solved for an initial value problem in section 2.1, with second order equations where there were two solutions, we often came up with a system of two equations in two unknowns, but here we have three equations in three unknowns. And you could solve these any way you like. I'm going to label these just for the sake of showing the rest of the solution. 1, 2, and 3, Roman numerals I'll choose. And I'm going to use, if you use Kramer's rule, or if you use Gaussian elimination, from linear algebra, whatever way you want to solve these is fine with me. But I'm just going to assume that we haven't all taken linear algebra, and I'm just going to do it the old-fashioned way. So what I'm going to do is I'm going to take equation 1 and 2 by elimination, basically. So I'm taking equation 1 and 2, and recopy them. C1 plus C2 plus C3 is 0. I like to put the variables on the left. And C1 plus 2C2 plus 3C3 is 0. And then I'm going to choose to eliminate the C1 by multiplying the top equation by -1. So then I get negative C1 minus C2 minus C3 is 0, and C1 plus 2C2 plus C3 is 0. Then adding the two equations, we get C2 plus 2C3 is 0. So there's now an equation with two unknowns. And now I'll take equation 1 and 3 again, and eliminate the same variable, C1. So there's 1, here's equation 3, C1 plus 4C2 plus 9C3 is 0. And again, I'm going to multiply the top one by a -1. And you could do this any way you like, as I said. Okay, so we get negative C1 minus C2 minus C3 is 0. And just recopying C1 plus 4C2 plus 9C3 is 0. Adding those two equations, we get 3C2 plus 8C3 is 0. So there's another equation with the same two unknowns as the original. So if you want to label this 4 and 5, if you like. And now using 4 and 5, C2 plus C3 is 0, and 3C2 plus 8C3 is 0. And then if I multiply the top equation, let's say by, I copied that wrong. It was C2 plus 2C3 for equation 4. And then if I multiply the top equation by -3 to get rid of C2, then I have minus 3C2 minus 6C3 is 0, and just recopy 3C2 plus 8C3 is, that was 3. I made a mistake up here, I'm sorry. So the C1 plus 4C2 plus 9C3 was equal to 3. So, okay, so let me fix these. It's not too big of a deal, I apologize. But those become 3s, so that was a 3, a 3, and a 3. That makes this a 3 as well. Okay, so now we can add the two equations, and we get 2C3 is 3, so then C3 is 3/2. Okay, and then we just work our way backwards to find the remaining constants. So from equation 4, we have that C2 plus 2C3 is 0, and C2 plus 2C3 we found to be 3/2, must be 0, so that'd be C2 plus 3 is 0, so C2 is -3. And then finally, let's go to equation 1 to find C1. And we had C1 plus C2 plus C3 is 0. So C1 minus 3 plus 3/2 is 0. C3 is 6/2. So -6/2 plus 3/2 is -3/2. So C1 minus 3/2 is 0. So C1 is also positive 3/2. Okay, so then our final particular solution is y is C1, which is 3/2 e to the x, plus C2 a -3 e to the 2x, and then plus C3, which was 3/2 e to the 3x. Okay, so I think I'm going to stop right there for this part. This particular lesson will be in multiple parts in terms of the videos, and so we'll come back and we'll do part 2 next.